What is the role of KL divergence in VAE reconstruction loss? Imagine trying to teach a computer to generate new images or data that look real. Variational autoencoders are one way to do this. They learn to compress data into a small, manageable form and then recreate it. But how do they make sure the compressed version is useful for creating new data? That's where the KL divergence comes into play. In a variational autoencoder, the goal is to encode data into a latent space, which is like a hidden map of features. The decoder then uses this map to reconstruct the original data. The training involves two main parts, the reconstruction loss and the KL divergence. The reconstruction loss checks how close the output is to the original data, like how well a painter copies a picture. It makes sure the generated data looks similar to what it learned from. But if the model only focuses on copying data well, it might end up memorizing specific examples. This can make the latent space messy and overfit the training data. It might not be good at creating new, unique data or generalizing to new inputs. That's where the KL divergence helps. It measures how different the learned distribution of the latent variables is from a simple, predefined distribution, usually a normal distribution with a mean of 0 and a standard deviation of 1. By minimizing the KL divergence, the model encourages the latent space to be smooth and organized. This means the encoded data points are spread out in a way that makes sense and is easy to sample from. It prevents the model from overfitting by avoiding irregular or overly complex encodings. Instead, it creates a balanced space where new data can be generated by sampling from anywhere in the latent space, not just near the training examples. Think of it like organizing a library. Without proper arrangement, books might be randomly placed, making it hard to find or add new ones. The KL divergence acts like a librarian who arranges the books neatly, so new books can be added easily, and the collection makes sense. This organization allows the variational autoencoder to generate new, realistic data that fits well with what it has learned. In applications like image generation, this balance is vital. It helps produce images that are both diverse and coherent. The KL divergence ensures the model doesn't just memorize but learns a structured, meaningful latent space. This structure is essential for creating new images, like those from DALL-E or Midjourney, that look fresh and convincing. Understanding the role of KL divergence also touches on ethical AI practices. When the latent space is well regularized, the model is less likely to memorize sensitive data, reducing privacy risks. It also promotes responsible use of generative AI by making sure the outputs are not just copies but new, original creations. So, in simple terms, the KL divergence acts as a guide for shaping the latent space in variational autoencoders. It balances the need to accurately reconstruct data with the need to keep that data organized and easy to sample from. This balance is what makes VAEs powerful tools for generating new, high-quality data in the world of deep learning and artificial intelligence.